morning, everyone. Welcome to the last day of the workshop. Today is about geometry in learning. And I'm very pleased to introduce Anthea, who is going to give the first bootcamp on the topic today. Please go ahead.
Thank you very much. Thank you very much to the organizers for organizing this lovely event and inviting me to speak today. It's very lovely to be here. I mean, I've been awake since 2 a.m., but it is still very lovely to be here. So I was asked to give this sort of overview or a bootcamp kind of talk on geometry and graph learning. Graph machine learning, but when I was planning it, I found it very difficult to focus only on geometry. And so I'm actually going to be talking about geometry, topology, and algebra. And they're for two reasons. One, I hope to convince you today that these three types of mathematics are actually very intimately linked in the context of machine learning, and especially graph machine learning. So you cannot have one without the others. So hopefully, you'll be convinced of that by the time I finish my talk. And then the second one is basically shameless self-promotion, because this is the kind of area that I'm working in. So yes, so let's get started. So let me start off by motivating why we need mathematics and these kind of mathematics in graph machine learning specifically. So why do we need structure-aware graph machine learning, right? So we're looking at graphs here, right? So this whole workshop here has been about graphs. So they really, they show up everywhere, right? And it's a universal language for connectivity, right? So what do I mean by graph here in the sense? So we have an abstract mathematical object, which consists of vertices and edges. So vertices are abstract points, which represent entities, and then the edges are the connections between these vertices, which represent relationships. So the little asterisk that says, for now, this is how I'm going to think of a graph, right? So we focus on abstract graphs, right? And the way that the vertices are connected is what matters, right? So here, the structure here becomes really important because we have an example here of these three graphs with identical node degrees, but they're non-isomorphic. So we need something that captures the structure as well, right? So what I want to argue is that combinatorial representations of graphs, such as vertices, edges, subgraphs, and these kinds of concepts alone is not enough to capture key differences in shape, symmetry, and geometry. Okay, so like I said before, I believe that geometry, topology, and algebra are very closely linked when we're considering graphs. So really, let's consider sort of three lenses on graphs here, where we look at geometry, which treats graphs as metric spaces or manifolds, right, and develops tools to, from this kind of geometric viewpoint for graphs. Topology treats graphs as shape, and we encode them by connectivity or higher homology, right? And then algebra treats graphs as objects with symmetry, invariance, and spectral properties. And there's ways to look at graphs from these three perspectives and enhance learning techniques in a way that's quite powerful. Okay, so let's look at graph neural networks, right? So this is the whole sort of like topic of this whole week long. So I'm sure you've seen this a lot by now, but I still want to sort of go over this and just so that we're all on the same page about why we would want to study these three types of mathematics in this setting, right? So we have graphs, we have these vertices and edges and their connections, right? So message passing is a way for nodes to share and update information by talking to their neighbors, right? So in rounds. So the idea here is that you send messages, right? So each node computes a message based on its own state, right? And then its neighbor states, and then you share information, so you're aggregating messages, right? And then the node collects all of the incoming information from its neighbors, and then aggregates them somehow, so for example, by summing, averaging, or taking the max, and then you update its state, right? So we have these GNNs, right? And there's this quote that I like here, right? It says that while GNNs have the ability to ignore the graph structure in such cases, it's not clear that they will, right? So there's this paper here, right, that's basically saying in this work, they show that GNNs actually tend to overfit the graph structure in the sense that they use them even when there's a better solution that can be obtained by ignoring it, right? So Here, this is saying that GNNs, right? They're very powerful, right? But there's more that needs to be done with these kinds of machinery in order to sort of like say more about underlying structure. So GNNs are actually incapable of recognizing certain topological structure sometimes, and so there are ways that like been very active community so far of trying to sort of enhance them somehow using algebra, geometry, and topology. Right, so message passing is this predominant paradigm for graph machine learning, right? So as I was saying before, neighboring nodes can exchange messages, right? If this is iterated, messages can be diffused to larger parts of your graph, right? So the idea here is that message passing neural network is the idea of message passing with learnable functions for the message and the update steps, right? So the idea here, I try to think of this kind of like, I like intuitive ideas, right? So message passing is basically like neighbors exchanging gossip at each round. And then the message passing neural networks are basically when the gossip is crafted and interpreted using trainable intelligence, right? So this is...
Better or worse?
So yeah, I mean, like, yeah, message passing is very good, right? It's something that, I mean, there's no denying about the central role of message passing neural networks in graph machine learning, right? But there are limitations, right? So some of the very common limitations or well-known ones are these ideas of over-squashing, over-smoothing, and limits on expressivity, right? So this is where these kinds of questions about, like, enhancing these graph neural networks and message passing in particular with some geometric ideas can really help a lot. Right? So why would you bring in algebra, topology, and geometry for this? So these are kinds of mathematics where you can include local, global, robust, and expressive features. Right? So here, this is the idea to complement your GNNs and to try to make them more powerful depending on its purpose, not to replace them. Right? So we have a geometry lens, right? So as I mentioned before, you want to treat the graph as if it's a metric space, right? So distances and shortest paths, for example, or you embed nodes into a manifold and then study it using geometric tools, right? There's the topology, right? So here you're looking at combinatorial topological spaces with vertices, edges, one-dimensional simplicial complexes for graphs in particular, but of course you can abstractify to higher dimensions if you like. And then you can study shape features like connected components or cycles. So I'll talk more about this later on. And then the algebra lens is basically treating your graph as an algebraic object, right, with adjacency or Laplacian matrices, for example, automorphism groups, representation theory if you get more exotic, and then you study its invariance and its symmetries. So I hope by now that I've motivated why we're doing algebra, topology, and geometry. And then at my group at Imperial, we kind of take this to the next level. And we study algebraic topology and algebraic geometry. So I should mention by default, I'm not a machine learner, right? I'm a computational mathematician. I work in computational topology and computational geometry. And very recently, in the past couple of years ago, I've seen machine learning as a nice example of the kind of mathematics, like application area for the mathematics that I'm doing. So algebraic topology is, it's basically a way, I try, like, when I talk to people, who are obviously not this audience, but like, the general audience, general public, I try to say that, okay, topology and geometry are ways that you can sort of study shape. And algebra is a way that you can count things, right? So here we're trying to count shapes, count features of shapes. And I'm interested in developing methods and theory and tools in algebraic topology using algebraic topology and algebraic geometry to apply them to data and computational settings and sort of to motivate why these two fields in particular. So algebraic topology, it's amenable to data analysis because it studies features or these invariants, right, which are robust to smooth deformations. And you can see in real data, there's lots of noise, right? And noise can be seen as such a smooth deformation. So this is why it would make sense to sort of study algebraic topology in this sense. And then in algebraic geometry, the central object of study is what's known as a variety. And they're extremely flexible in general objects which can model many things, including real data, and also including neural networks, which I'll talk about a bit later. So this is my fantastic group at Imperial. So these are my PhD students and my postdocs. I also have master's students who are not included here. And we're funded by a £10 million grant from the UK government, which I won last year together with Michael Brunstein, one of the organizers of this conference who's not here today, and Jeff Jan-Siracusa, where we established a hub among 6 universities in the UK to study the mathematical and computational foundations of AI using exactly algebra, geometry, and topology. So, okay, so that's what we do. Okay, so graph theory. This was motivated, so there's this famous, this is sort of like the foundations, the birth of graph theory, right? So there was this famous problem about the 7 bridges of Königsberg in Prussia at the time, and the solution was founded by Euler in the 18th century. So the question here is you have this sort of city here, right, Königsberg, with islands and so like islands and land, and then you have bridges, like a sequence of bridges. And now the question is there a walk through the city that crosses every bridge exactly once? And this is the problem that laid the foundations of graph theory, because Euler noticed that the land masses themselves and the distances between the lands don't actually matter, right? The only thing that matters is the sequence of bridges being crossed, right? And so only the connectivity information is relevant. So this was the first kind of, configuration of a graph showing up, and then Euler showed that basically it's not possible to walk through the city crossing the bridge exactly once, because there's more than 2 vertices with an odd degree. So this is how graph theory started up, and moreover, this is also how topology arise, because here, when you're looking at only connectivity information, right, and you're not looking at things like distances or particular locations, right, this is also sort of the idea of topology here, right? So in topology, the idea is like, okay, you're looking at geometric ideas without a notion of size or location, right? So, yeah, this is sort of motivating the graph theory. And then in terms of topology, right, so this here you can look at sort of like graphs, so, motivating there. So going from this idea that the land masses are the only things that matter, right, this sort of corresponds to, your nodes of your graph, right? So in topology language, right, this corresponds to your connected components, or your Betti numbers, which are Betti 0. I'll talk more about that a bit later, right? Or cycles, right? So cycles also here is like a higher dimensional topology. Here you're looking at loops, right? So this is what topology is sort of all about. And then algebraic geometry and tropical geometry. So we saw a little bit about this in Christoph's talk yesterday, but as I mentioned before, algebraic geometry looks at the locus of zeros of polynomial systems, right? So you have a system of polynomials, you're looking at its solution set, and algebraic geometry, we care about the geometric features of the solution set, which can be described purely in algebraic terms. And then tropical geometry is sort of like a piecewise linear version of this. I'll talk more about this later. But the reason why I'm kind of introducing these ideas now was that because, like I said before, these 3 topics are so interrelated, it was very hard to sort of like talk about one without bringing in sort of concepts from the other one. So just keep these sort of like high-level ideas now about what I mean by topology, geometry, and especially tropical geometry. Okay, so let's start with algebra in graph machine learning. So why should we care about algebra in graph machine learning? So in graph machine learning, we want to respect symmetries of data, right? So algebra shows up in 2 flavors, right? So one is linear algebra. This is something that we all know and love. We're looking at things about, vector spaces, matrices, and transformations. These are all, great things that we're very familiar with. You can go more exotic as well. So you can look at more sort of abstractifications in terms of algebra, in terms of groups, rings, semi-rings, fields, and algebras. And right, so in terms of these symmetries that we care about in graph machine learning, algebra is really the language for describing them. So, right, when I say in graph machine learning, many models are really algebra and geometry sort of together, right? So in this case here, geometry gives us the space, right? And then algebra encodes the transformations, right? So graphs, manifolds, and other kinds of structured objects aren't just the geometry, right? It's not just the geometry here. They also have operations which respect structure. So with using algebra, we can describe and manipulate these operations systematically. Okay, so in terms of algebras and the more sort of like abstract algebra, right, we're thinking about groups. So groups are really central to encoding symmetry, right? So what do I mean by a group, right? A group is a set of transformations that leave the sort of structure of the problem unchanged. And in machine learning, right, we care a lot about equivariance and invariance, right? So equivariance is a bit more general here, but group theory is really central in equivariant models, and what's really the key mathematical tool to describe this, right? So in equivariance, right, the idea is that we apply symmetry to an input, and then the output should be able to, it should transform in a way that we can predict, right? So it should be predictably transformable. And then I mentioned that there's more exotic stuff. So there's some representation theory, tensor algebra, Lie groups algebras, category theory. It's a really exciting space for some quite cool mathematics to show up here. But maybe let's go to some examples first, right, to sort of motivate why we care about this. So graph automorphisms, right, these are showing up in GNNs a lot, right? So this whole conference is about GNNs, and graph automorphisms are a key concept here, right? So graph automorphisms for a group, right? So GNN layers are often designed to be invariant, right? Right, to this group's action. And so the idea here, right, is that you have a group because identity, right? You have the identity because doing nothing is an automorphism itself, right? You also have an inverse because reversing a relabeling sort of gets you back to where you started from, right? Closure, you need closure, right? So composing two automorphisms gets you back another automorphism, so you have closure here. And associativity, right? So function composition is associative. So the set of automorphisms is called the automorphism group of the graph, right? And right, you have a connection to GNNs because you have permutation. You want permutation equivariance or invariance in designing your GNNs here, right? So it basically, the group structure of these automorphisms here formalizes the symmetries that a GNN has to respect, right? And algebra gives us basically a rigorous way to describe them, symmetries, and then reasons about architectures and ways that you can sort of preserve them in your GNN. And then semi-ring algebra, right? So here's another sort of algebraic flavor here that we have, and how it shows up in the context of graph machine learning, right? So this shows up in message passing on graphs, right? So they're designed to be invariant or equivariant to the action of the automorphism group, right? So, so it's either a GNN or a probabilistical graphical model, right? So the idea here is that you have information from the neighbors being repeatedly aggregated, right? And so the aggregation happens over a semi-ring, and so in the semi-ring we have a notion of addition or multiplication, which we can sort of define in a particular way. So I'm going to talk more about this later on, which satisfy certain algebraic axioms that we would like, right? So, this depends on what we would like to do, right, with our message passing. But for example, in the sense of belief propagation, you would have the sum product semi-ring, and then for max a priori inference, right, you would look at the max sum semi-ring here. So you can have, this is flexible because you choose your algebra, right? You can define, as I mentioned before, what your semi-ring algebra looks like to adapt to your message passing here, right? So these are two examples where algebra comes up. Okay, so now how do we go to, let's move to geometry, right? Or algebraic geometry in graph machine learning. So I'm only going to focus on two types of geometry. There's more concepts of geometry as well, but the first one that I'm going to mention here is sort of metric spaces. So the idea about our graphs, right? Why would we, look at metric spaces, or what's the idea behind this? Well, we have certain challenges about graphs, right? So graphs themselves are not metric spaces, right? Natural metric spaces, unless you sort of define and endow a metric, right? So the most common one is probably the shortest path metric. These are non-Euclidean objects. You can have different numbers of vertices as well. So the most standard way to handle this is you looking at a vectorization, right? So you have a vectorized representation or an embedding, and you need this to be permutation invariant, right? Because of all the thing I was talking about for the algebra, right? So, right, so there's ways that you can do this, right? There's like some shallow approaches which include node to vec or graph kernels, and then other sort of like deep learning approaches, so graph convolutional neural networks and these other kinds of graph networks here. So. Yeah, so what's the idea behind these vectorizations or this embedding graphs, right? So you want to move from a discrete setting, right? Our graphs are discrete geometric objects to a continuous setting, right? So you assign each node a coordinate in a continuous space, metric space normally, that reflects the graph structure, right? And what's commonly used are manifold embeddings, right? So real-world graphs, they're hypothesized to have some kind of latent structure which are low-dimensional and curved, and manifolds are sort of like good settings, sort of hypothesized to be good settings for this. So I became very interested in this idea here because I was interested in hierarchy, so in particular trees. So trees are sort of like, I'm looking at a particular kind of graph here. I've worked quite a lot in biological applications before where I was looking at phylogenetic trees. So phylogenetic trees here are particular types of graphs where each of the lengths on the trees have edge weights, so non-negative edge weights from them. And so sort of mathematically, there was a motivation for me to look at a more general setting where we're looking at hierarchies, right, where the edge lengths don't matter, but the hierarchical structure does. So yeah, this sort of like led me into this sort of like machine learning literature here where I saw that there's a very common way to, like the current strategy to do this is to, in particular this paper here, embeds them into a Poincaré ball, right? And then basically has a metric on this ball and try to sort of like compare objects or entities in this setting here. So this is kind of problematic because it works when you have a tree, right? So the lexical hierarchy will work in the setting, right? But if you're trying to do it with a graph, so some of the work that I've worked on before shows that the topological structure of the graph is not preserved when you do this kind of embedding here. So this motivates sort of different perspectives. So something that I'm currently working on or have been working on is basically working directly in the space of hierarchies, right? So this is sort of developing what I call non-Archimedean machine learning. So these hierarchies that I was talking about before, they lie in fields which are known to be, that are called non-Archimedean fields, right? So the idea here is that intuitively, small things in this case dominate everything, right? And the notion of size is really quite intuitive because you have a strong version of the triangle inequality here. For those of you who are sort of maybe more mathematically inclined, an important example of a non-Archimedean field are the p-adic numbers, right? So here it's very different because it comes up in number theory a lot, the p-adic numbers. And the idea here is that instead of the traditional way of sort of focusing on the left part of the number before the decimal place, the p-adic numbers focus more on the furthest right? So after that, right? So when expressed in base p, right? So they basically provided an alternative way of measuring the size and closeness of your numbers, right? Particularly on rational numbers, using a different non-Euclidean metric. Yeah.
I think later in the bootcamp where you give us examples of what kind of insights this kind of embedding gives us?
No, so I'm not going to. This is still like, this is still sort of ongoing work, but I'll be happy to sort of like talk to you and like, sort of give you examples. I mean, one thing that I can tell you here is that this actually kind of makes sense, right? But first, and we can actually do things with this. So we have code for this that works, but so maybe first I'll sort of like motivate that and then we can, maybe see if it answers your questions. But so the idea here is that, okay, let's, instead of mapping our structure into a manifold, right, where you could lose some information, right, like I was saying before, right, if you're doing it with graphs, you lose the topology of the graph. So the topology of your graph is not respected. So the idea here is like, okay, we have a space where you can do this directly. So let's try to do it there. Question?
In the previous slide, the paper that you mentioned, is that the paper that does the embedding in the hyperbolic spaces?
Mm-hmm.
And you're saying if you do the embeddings in the hyperbolic spaces, it doesn't maintain the geometry.
If it's a graph, the topology of graph, so you lose some of the cycles. It works for trees, but if you're trying to do it for graphs, then there can be problems, right? Yeah.
Is that the picture of the non-Archimedean embedding?
No, so this here is actually a Berkovich analytification about it. So I'm going to talk about this first. Yeah, questions?
So if you have a graph, what algorithm are you applying to it in order to get an embedding, for example?
So the one that I mentioned, or the one that I was studying before, was this paper by Mikel and Kiela from 2017.
Yeah, but for the Dianic case, what would you do to it?
So I'm talking about that right now.
Okay.
Right. Okay. So we are, we have this field, right? We have this non-Archimedean field. This is inherently where hierarchies live, right? This is the natural space where they live, right? And the way that people have been working with them before, dealing with sort of complicated objects where they don't know what to do, they embed them into manifolds, right? Because we understand manifolds, we have machinery for manifolds, we have tools for them, right? But I was saying before, I argued that, this can be problematic, right? You can lose some sort of structure of your original data if you do that, right? So the idea here is like, why don't we just do it in the original space? But this space is hard to work with, right? So these non-Archimedean fields, right, there's a problem. So they're totally disconnected spaces, right? So how are you going to do things like gradient descent, right, if you want to do machine learning, right? So this is really difficult. You also have things like locally constant functions may not actually be constant, right? So then how do you do optimization? So the way people in analytic number theory have been working with this, right, with the p-adic numbers, is that they do this thing called Berkovich analytification, right? And the idea here is what they do is they, over your totally disconnected set, right, I mean your totally disconnected field for each point, they grow a ball, right? And then you have like a sequence of overlapping balls, and now you have something that's path connected, right? So so essentially the idea here is basically Berkovich analytification, and it can get quite wild, right? So here this is an example from a non-trivially evaluated field, right? So this is not the case that we would be looking in for real data, right? But this is basically, you have this kind of tree structure with infinite branching at each of the nodes, right? It can get quite wild, but they're very fascinating objects to work with. And people in analytic number theory work with this quite a lot. But in the case where we deal with hierarchies, like especially if we, with the kind of data that the word hierarchies that I mentioned before as an example, we can do this Berkovich analytification. We come up with what we call a polydisk space. So the preprint is coming if you're interested for more information about that. But the idea now is that we have this sort of like, by growing these balls, we have a space that's path connected. And then what we've shown there is that we have global minima, right? So we have stable centers, right, in our non-Archimedean fields. And then we've also shown that it's also true that if you have stable centers, you can get global minima when your valuation on K is dense, right? So essentially the idea here is that everything, all of this sort of ideas of valuations and denseness of valuations is just basically a way of sort of like assigning size, like a concept of size to non-zero elements here. So we get some foundational results here in terms of like maxima and minima, right? If you're going from the perspective that everything in machine learning is an optimization problem, we have code for this that works. We have also applied it to some real data. So this is some stuff that we're working on. Hopefully, the preprint will be out later on this year.
So just a curiosity, does it exist some analog of, you can work with some analog of Lipschitz functions with the valuation instead of the distance?
You can.
These balls seems like, it seems that the approach is that of studying the dual of this space, in a sense, right? These balls are, in a sense, like you're studying the functions of the space rather than the space.
Yes.
Because you have a notion of...
Yeah, but I'm not sure I would exactly call it dual, or maybe you're thinking of dual in a way that I think of dual as different.
Space versus the functions of the space.
Yes. Okay. Yeah. I mean, that's one way that you can look at it, right? Like
So then the question is, would be a kind of nice functions that are kind of well behaved for this kind of not metric, but valuation.
Yeah, so I mean, in this case here, we're not, I mean, we don't actually study it from the dual perspective, right? Like we didn't study, I mean, like, yeah, I mean, I agree with you that if you're looking at it in terms of like a sort of functionality here in this case, and there is that kind of concept from dual that you're looking at here, but here in this sense of like the Berkovich analytification, as far as I'm aware, that's not how they look at it, right? The idea here really is basically just growing these balls so that we get this path
But
connectivity.
in a sense, if you do learning, then you are working with some kind of function.
Yeah,
Yeah. Okay.
yeah. But we just don't, we don't consider it from the perspective of duality here, right? We're just like looking at,
No, you don't.
Yeah.
You don't have.
yeah, you don't have to, right? I mean, I am actually very interested in dualities, right? I mean, you know, or we can talk later, but I'm not sure, I don't remember if I'm actually going to talk about this stuff later on, but I mean, at least from what I'm working in the kind of like, maybe the non-machine learning case, but has very important implications on machine learning, is that dual perspectives, right? So if you're looking at like cohomology, for example, this has very, very important implications on computations, right? So it turns out that, so in another algorithm that I'll sort of talk about later on, the currently fastest existing algorithm computes cohomology instead of homology. So yeah, it's a point.
Will you aim at an approximation results, a kind of universality in some sense?
Yes, we do. We actually have that. That's a good question. So yeah, that is something that we actually do have, that collection that we're writing on.
And more or less how that is formulated?
So the exact statement of the theorem depends on the polydisk space, right? Which is kind of like a special case of this Berkovich analytification. So there are some sort of technical examples about that I think maybe in the interest
in order to talk to the rest of the kind of standard this approximation theory community, maybe it would be useful to have this rewriting polydisks as similar to
Yeah.
functions.
Yeah. Well, we're trying, right? Like the idea is basically to make this, you know, as user friendly as possible to sort of like talk to the community who wants to do this kind of stuff. So yeah. Okay. So yeah. I think, so this is something that I'm quite excited by, but I think what I want to say or sort of motivate to all of, you know, the sort of machine learning community here, right, is that there is very cool exotic mathematics here, and I think it is worth it to explore it for the kinds of problems that we care about in machine learning. Yeah, I think mathematicians should be talking more to computer scientists and machine learning researchers because of this. So. Okay, so the second kind of geometry that I want to talk about is curvature, right? So as I mentioned, there's a lot more than just these two, like than just the embedding and the curvature here, but these are sort of like for particular reasons that I'm picking this, yeah. So we want to characterize how curved an object is, right? So, you know, this is sort of the whole idea and motivation behind defining some kind of curvature. And curvature can be extrinsic or intrinsic, right? So extrinsic curvature here means that, you know, your curvature relies on the embedding space that you're targeting to, right? So this kind of idea can change depending on which space you're mapping to. Or it can be intrinsic in the sense that it's a property which is really preserved by the object itself, and it doesn't matter about what embedding space you're looking in. So Gaussian curvature is pretty much the classical one, right? Is maybe the first idea here, right? Right, so this is like examples here of like what Gaussian curvature looks like, right? I mean, hyperbolic spaces, flat, spherical cases. And the idea is, can you discretize this and adapt it to graphs? And the answer is yes. So there has been quite an active community working on discrete curvatures, discrete geometries in particular, to adapt them to graphs. And I think maybe probably one of the most famous adaptations here is the Olivia Ricci curvature here. And you can sort of see how, right, going from the Gaussian curvature below, you can sort of adapt it to this sort of graph setting here with this kind of these kind of pictures here, where the idea here now is that flatness corresponds to lattices. The hyperbolic structure would be something in terms of trees, and then you can have like simplicial complexes for positive curvature, things like that. So Yeah, so Olivier-Ricci is probably one of the most famous curvatures, but there are also other discrete curvatures that have been studied very actively by the community. So there's the Foreman curvature, right? So I'm looking at the 1D, but there's like lots more, sort of generalizations of this, including the augmented Foreman curvature, Hanti's curvatures, or these other things. And so this idea of curvature and the classical sort of curvatures has been used to rewire graphs. And so this is basically trying to sort of regulate the information over squashing problem that you get with message passing GNNs, right? So there's been a paper by collaborators, including Michael Bronstein and people in his group in 2022, where they propose a new notion of discrete curvature, which they call the balance Foreman curvature for graphs. And then they also propose a stochastic discrete Ricci flow to smooth the graphs, right? So the idea here is like when you have a graph, which has a kind of bottleneck where you have a highway, right? So you have a lot of information being passed along from like one sort of group of the graph to another one that's going along this one edge here, right? You can get information which is kind of over squashed here. So the idea about rewiring graphs is sort of to identify these bottlenecks and then add more edges around there to support the information flow. So we found this really cool and interesting, especially because I was very interested. So as I mentioned, my area is in discrete geometry. I was really interested. I work a bit in discrete curvature. And so we took their paper, their setting, and then we discovered these other discrete curvatures that I happen to work with and know a bit about. So we tested it in this problem of graph rewiring, and we showed that we get, so on this left table here, in terms of accuracy, node classification task here, right? It's just as accurate as the new balance Foreman curvature that they proposed, right? So it's on par in terms of accuracy, but it's much, much faster to compute. So on the right here, this is a runtime in seconds about how to compute. So the BFC is a balanced Foreman curvature, and we see that in terms of the other discrete curvatures, the classical discrete curvatures, they're much faster to compute. So if you want something that is just as accurate but faster, you can use these sort of more classical ones. And this basically shows that I think the real, the takeaway message here is that the real sort of contribution, the real powerful contribution of the topping paper is the stochastic discrete Ricci flow. So again, I think the message here is that there's cool kinds of mathematics, right? There's a lot of mathematics which can be used to enhance your graph neural network and learning problems here. Yeah.
But could you just get this with standard graph theory? I mean, these insights that you have this edge that connects these dense components. Do you really need the tools from geometry to do this?
So you mean to rewire, right?
Yeah. I mean, it seems.
They're all graphs, right? And so, yeah, you can. I don't know. What particular type of theory from graph theory that you would want to use to identify these highways and support more?
There's all these studies of conductance and so on.
Yeah, you could. Yeah, for sure. There is for example, there's some work done by Renaud Lambiot at Oxford that uses effective resistance. This is a concept from engineering and physics that's used quite a lot. They have a whole, one of his students also, Carl de Vriend, also works quite a lot in looking at these kinds of effective resistance stuff, these more physics-inspired things. So
does it give you anything?
I haven't actually particularly studied these physics approaches, right? So
for example, these approaches you were talking about, does it give you anything above just using standard graph theory tools?
Well, so
in
here.
This setting.
So in this setting, right? We've shown that this is powerful, right? This is something here where you can alleviate this message. The over squashing problem in this case using the geometry. But I think to answer your question, what we would need to do is then do a case study against effective resistance, for example, right? And that, as far as I'm aware, has not been done yet. So, in principle, I'm not, opposed to that idea. I just don't know enough physics. I would be open to learning it. I think that would definitely be an interesting study. You're kind of benchmarking geometry approaches against, physics or engineering or something. Maybe in that case you can just use standard graph theory. Sure.
This approach would be very favored in case you have a graph that comes already from sampling something like a surface, a manifold, and so on, because then it can be interpretable in the initial setting, right? That's an advantage for sure if in a specific set of graphs.
Yeah, I think it depends on where your graph comes from and what you're trying to model, right? Or like where it comes from. You know, like, I mean, a particular example might be some stuff that I'll talk about later, but we've also seen yesterday in one of the talks, right, where you're looking at what traffic networks, right? Like transportation networks here, right? Where you're looking at some sort of underlying space, right? Where you have like, you know, roads, which are basically kind of predefined, and there's some kind of geometry here to respect. So, I mean, I don't know if graph theory would be better in that case or not, but, you know, I just don't know. I mean, I'm not very familiar with the graph theory, like purely graph theory approaches to machine learning.
Because every time I read those papers, I thought like, well, okay, that seems like a, you know, kind of a large hammer for a pretty simple problem.
Yeah. I mean, I should mention though that the stuff that I'm aware of, as far as like, for example, effective resistance, right? There are connections that have been made to curvature already. So there might be some kind of like a, let's say, kind of infiltration already of sort of geometric ideas in that area. But I mean, I know that also effective resistance has already been like, you know, connected to other things, like which are purely combinatorial, like, you know, matroids or something like that too. So, you know, maybe possible. But I mean, as far as I'm aware, maybe other people here know, I have not seen that kind of approach being used here. But I think it would be an interesting thing to study and say that, like, okay, this would be, you know, a way to sort of say, okay, does geometry really matter in this case or not? And I mean, my intuition there is probably, in some cases, maybe not, but maybe in some cases, yes, right? Because exactly if what, you know, if your underlying space is a discretization of something that is definitely a geometric object, I think. Okay, so let's move on to algebraic geometry for machine learning, right? So this is something that I'm working on. So as I mentioned before, right, it is sort of kind of surprising, and when I talk to people in the mathematical community, especially pure mathematicians, I have to motivate why algebraic geometry, which is a very pure field of mathematics, should make sense in machine learning or data analysis or statistics. And so, yeah, as I mentioned before, relationships between data and geometric objects, they can be modeled by these varieties, right? So real data, I mentioned that I worked quite a lot with phylogenetic trees. So the set of all phylogenetic trees actually form a type of tropical, a particular type of algebraic variety, in particular tropical variety. So I've worked quite a lot in that. And then in synthetic data as well. So I consider neural networks to be like synthetic data. Of course, this is sort of like a matter of approach and perspective, but you know, if you think of sort of like neural networks trying to learn the way that a brain does, you can think of that as a sort of synthetic data. But anyway, the point is that neural networks, you know, there's a lot of these things. They can see their discrete geometric objects themselves, and there's an intimate connection, which I'll talk about. Well, we saw a little bit about this yesterday in Christoph's talk, but I'll talk about it more about how it's related to tropical geometry. They can also be used for perfect data. So something that I'm very interested in, and that one of my postdocs, Sarah, studies a lot, are Fano varieties, which are particular type of algebraic varieties. So the idea here is, as I mentioned before, varieties are basically just solution sets to systems of polynomial equations. So you can write down whatever set of polynomials you want, solve them, and then you get a variety. And then you just do this a lot of times, right? And then now you have like a whole bunch of a collection of varieties, right? They come purely from mathematical settings, right? But they are data, right? So there's no randomness here, but they are perfect data. So that's what I mean by perfect data. And, you know, why not use machine learning on this? And it turns out you can. So I'll talk more about that a bit later on, but yes, you can. So, yeah, so this area here, right, there's like some, not a lot, but it's kind of a new area of using machine learning to understand algebraic varieties. But then it turns out that algebraic geometry can also be used to understand machine learning, and we saw a glimpse of this yesterday in Christoph's talk. And there's been some work on this, not a whole lot, but some. So let's sort of talk about exactly how this comes up. Okay, so what is tropical geometry? So we saw this a lot yesterday in like ideas that looked very tropical, and I think that this is the language that we want to look at for studying neural networks. So we saw this in Christoph's talk yesterday. So what is tropical geometry? So it's based on the tropical semi-ring here, right? So this is a semi-ring. I'm looking at max plus algebra. You can look at min plus as well, right? It's basically just the idea of turning it around here. But I started off being interested in max plus because when I was studying phylogenetic trees, and there's some kind of stuff there. But yeah, I mean, the idea here is like if you're coming from algebraic geometry, they're the same thing. So you don't have to I mean, it's a bit of a way, sort of like a convention of sort of like messing with your brain a little bit. But yeah, I mean, they're the same thing, so you don't have to worry about it too much. But okay, so in the semi-ring, right, we have all the sort of basic properties, well, most of the basic properties, right? So right, we looking at the addition of two elements is just taking the max between them, right? And then the product here is just the regular sum. So we have basic properties, right? We have operations that are commutative, they're associative. We have an additive identity, negative infinity. We have a multiplicative identity, which is 0. The multiplicative inverse exists, the additive one does not, right? So the multiplicative one is just basically the negative of any value except negative infinity here. And then the additive inverse doesn't exist in general, because in general you can't recover the smaller two elements under the max operator using only tropical addition, right? So this is why it's a semi-ring, not a ring. For the, yeah, so I mean, you can kind of get an intuition already here about why people would care about this in computations and maybe even in machine learning, right? So here, this is basically ReLU activation. We saw this yesterday already. But here you're taking everything, you're turning products into sums. So it's linearizing, and you're just taking maxes. So you can imagine that this is very, very fast. And it does turn out to be actually very fast, right, in terms of computations, right? So this is why people in computer science and computations care about tropical geometry, but even mathematicians, like pure mathematicians, also care about tropical geometry because a lot of problems in real algebraic geometry or even complex algebraic geometry can be translated to tropical geometry, solved there, and then the solution maps back, right? And this is because you get weird, unintuitive geometries in the tropical setting, right? So similar to what I was showing before about the non-Archimedean fields, right? Here there are things that that kind of mess with your brain that don't work out, but this is exactly why it works when you're trying to solve problems to map back to real algebraic geometry, right? So for example, a couple of things that I like is that the tropical row and column span of any matrix, right, it doesn't have to be a square, any matrix are equal, right? So this basically means that you can solve problems depending on whether you care about looking at the rows or the columns of your matrix. The tropical convex hull over rows and columns is also equal, right? So the column span of a full rank rectangular matrix also gives rise to very different tropical constructions, right? So if you're looking at, I think it was the columns, or no, it's the rows, I think, you get Pluger equations, and then in the columns, I believe, or maybe the other way around. Anyway, the idea here is basically you have very different tropical constructions depending on how you're looking at your matrix, and you can look at rectangular matrices here. So you have this weird, unintuitive geometry. It's very nice, and it's very, very useful both in computations and in theory. Okay, so with these tropical operations here, right, you can define, regular sort of like mathematical objects, right? So you can write polynomials, right? So like some people might think of like tropical geometry as like the version of algebraic geometry where you're looking at solutions to systems of polynomial equations where the polynomials are written with the tropical operations instead. So yeah, so basically you have these polynomials now, and then the thing that people care about are looking at these tropical hypersurfaces, right? So it's formally defined as the max, the set where the max is attained by at least two monomials of f at x, right? Or equivalently, you can look at the boundary between regions of the domain where the tropical polynomial is linear. So in this case, the ReLU activation would be this 0 set here. So yeah, so this is what maybe sort of the most sort of standard way of looking at tropical varieties would be, but you can sort of like then for more sort of complicated, more general objects as well with tropical geometry, right? So into these, like in particular, the tropical rational functions are going to be important, and the tropical Puiseux polynomials are as well, right? So here you can think about these tropical Puiseux polynomials where the case where you have rational exponent, right? And then there's like sort of like some more theory that's that comes up in that case here. Okay, so there's this paper, this very nice paper by Lekheng and collaborators from 2018, which basically says that you can get a tropical representation for all ReLU neural networks. So here it's, actually what I mean is that you have a fully connected MLP, and you can write it in terms of a tropical rational function. And this is because what you're looking at here is this kind of expression of like maxes of, kind of linear functions, and then with these kinds of tropical operations here, which looks quite nasty, right? But again, just remember that everything here is basically products and sums. Some products turns into sums, and then addition turns into maxes. And then the idea here is that basically you can just reiterate this for every single layer, and then compose them, and then it turns out that you get this this tropical representation, right, in terms of a tropical rational function. So, I mean, if you think about it, this kind of makes sense, right? Like, I mean, you try to think about it, right? Like, so in sort of classical mathematics, it's known that you can get a wide class of functions represented by a difference of two convex functions, right? And then it makes sense that a neural network can be approximated this way or modeled by this way in terms of a tropical rational function, because neural networks are designed to model very complicated probability distributions, right? And then tropical rational functions are just the difference of two tropical polynomials, and they're convex, right? So in this case here, it's sort of like, I mean, this is like been formalized in this paper by Lekheng and collaborators, but it is something that shouldn't be so surprising. So there's some work that my student Shiv has done, right? So you don't need just ReLU activation, right? You can extend it to other activation functions, and you get another tropical representation as well. So the generalized step ReLU is another activation function where it works for leaky ReLU. This is particularly important in the vanishing gradient problem. It also has a tropical representation. Yeah, question?
Yeah, I guess, again, if there's something I can get about, it's similar to previous questions about feed-forward networks that doesn't mention the tropical summaries that I can get. I understand you can translate piecewise linear functions into polynomials by going into this perspective. And
Yeah.
then at the end you get some result, use some result in algebraic geometry, you can translate it back and get something new that you can phrase just in the original vocabulary.
Yeah, yeah. So, I mean, I think it's kind of a similar perspective. So, I mean, people in tropical geometry have done a lot of really complicated stuff, right? And this particular paper here, right, it's not, I mean, there's one result of that paper which uses some ideas from tropical geometry, but here it's just an observation here that you have an expression in terms of tropical terms for these neural networks, right? So now it's kind of like opening the door to say that, like, okay, you can use ideas from tropical geometry to then get some answers to questions that you would care about in machine learning. So one of the things in that paper, what they do is they count the number of linear regions, right, using tropical geometry. So we saw a little bit about this yesterday in terms of looking at Newton polytopes, right? So they look at sort of like subdividers, they lift it up and then do some sort of manipulations, do a projection, and then using some theory from tropical geometry, they got an analytic upper bound for the number of linear regions of your neural network, right? Which is what people would care about, right, in this community. Or I don't know if that answered your question, but the idea here is like, at least between real algebraic geometry with tropical geometry, they care about this kind of relationship, right? And I think what I'm trying to argue, or what this paper argues, the paper by Lekheng argues, is that you can also do this for machine learning, for people who study neural networks. Right? Yeah.
I'm not sure I understand exactly how it works, but if I'm trying to translate ReLU network into tropical geometry, so how do I translate the matrix vector multiplication, which is, because what is usually multiplication isn't there, right?
Yeah. I mean, essentially what you have is basically this sort of complicated construction here, right? This is what it looks like, right? But
But you need to assume like the matrix has natural numbers in it, like integers or something?
Yeah. Because the tropical semi-ring is the real numbers, right? But you need to have negative infinity for all the things to work out. But it's the real numbers, so you're...
No, but, okay. But I mean, if I'm want to multiply, pi by some number in tropical, and I want to translate that to tropical geometry, so can I do that?
Yeah, I mean, it's just a number, right? So pi here is one of your elements, right? In your semi-ring, and your semi-ring here is a real number, and pi is a real number.
No, but you don't have your multiplication is addition, and I mean, you don't have multiplication, the standard multiplication in your...
So, but maybe I'm not understanding the question. Like, the question here is like, well, if you want to multiply pi by something, right?
Yeah.
You can just take any two elements, right? So pi is in the real numbers, and then, right, you multiply pi by, I don't know, whatever, 1, 2, whatever,
So I
right?
want to multiply
And then it's...
pi by some other, by e. So is that like...
So
in
pi is the
standard
bigger.
sense?
So pi is the bigger number here. So, no, sorry.
No,
Multiply them.
standard
So you would add them. You would add them. In this
No,
case,
but I
right?
want to do standard multiplication, so can I express that in the tropical geometry?
Go
Can I
ahead.
say
Yeah.
something about- I guess the solution is that the matrix weights are in the exponent. These are tropical exponents now, because classical multiplication will be exponentiation in the tropical
Yes.
exponents.
Yes.
So that's why you see these a, I, j in the exponents of this formula.
Yeah.
You mentioned yesterday that you have also result that says that unions can be expressed as tropical functions, where you have like a region counting bounds for unions.
So I know I don't. Yeah. No. This is something that's like it's open work. It doesn't have an actual preprint yet, but this is something that I'm actively working on. So I'd like to do that. I'm hiring a postdoc also in case anybody's looking for postdocs to work on that. But yeah. But the region counting, I'm going to get to that later on because, yeah, exactly. That's sort of what I mentioned. So one of the punchlines of the Zhang paper, in the ICML 2018 paper, is they got this analytic upper bound for the number of linear regions, right? Yeah.
Can you go one step back to this generalization to other activation functions? I'm wondering, can you also get something like a meta result as soon as your activation function is continuous in pieces and you have finally many pieces, you can generate this somehow?
I guess so. Yeah, I didn't think about that, but this was, so my student Shiv is the one who did this, and so he did this in his master's thesis, where he basically looked at these two different activation functions, but we didn't think about looking at a general case here. But I mean, I think that would be
possible, I guess.
Yeah, I think so. It probably would be possible, but yeah, at least I mean, Shiv is a very talented master's student, but again, he was just a master's student, so I just told him like, let's take a look at other activation functions, and turns out that he wrote down the proofs for this, and this is true too. But I think that would be an interesting, very nice framework to do for this. Okay. So time is going pretty fast. So I'm sort of going to gloss over this because I want to get to sort of other stuff here. But like, I mean, the linear region stuff, right? Like we sort of had a few conversations about this, and this was sort of already mentioned already. So I just want to sort of go over this very briefly, right? So linear regions is a measure of expressivity, right? This is what people sort of like who care about. I mean, this is a kind of one of the measures that is possible, and you know, you can count this using tropical geometry. And then the idea here is, okay, you know, what we studied was not just looking at the analytic upper bound of the number of linear regions, but the question is, okay, how does the number of linear regions change during your training of your neural network? And so then here you need to sort of go to sort of like more numerical methods, and you can do this with tropical geometry. And essentially the idea here was sort of like, okay, if you're doing sampling to estimate the number of linear regions, sampling in terms of statistics is an expensive procedure, right? So you want to be able to, I mean, ideally you would like to sample a lot, so you have a lot of information about your input space, but you also don't want to sample too much because it can be expensive, right? So then the question that we asked is that, is there a way that you can sample as few, I mean, basically reduce the number of samples that you need to be able to give you some guarantees, you know, about coverage, right? And it turns out that you can do this. So yeah, and then essentially with the symbolic approach as well. So if you're looking at tropical rational functions now as neural networks, you can also get exact numbers to linear regions by using the kind of like symbolic, yeah, you know, software and stuff from the symbolic computation community. So Oscar in particular is one of the libraries for that you can use. So yeah, essentially, I mean, Oscar is used really for like mathematicians. So this is not something that's optimized for like machine learning. So it is very slow. But I think that if you like writing code and you're interested in this area, right, then a lot can be done in terms of sort of like augmenting these symbolic computation approaches for machine learning, I think. Yeah.
Like from a computational complexity standpoint, are there any benefits doing this? Accountability regions compared to not doing using tropical rational functions?
Well, I mean, yeah, so like in this case here, because if you're looking at symbolic computation, you get exactness, right? So if you care about exactness, then that's an advantage. But like I said, this kind of stuff is not optimized. It's not fast, right? So, but I think it can be. I think it can be made a lot faster. Like if you like to sit down and just write a bunch of code, I think you can. Right?
But also from a theoretical point of view, does it give you anything? Like runtime?
Yeah, I mean, we didn't study runtime complexity, so that I don't know about, right? But maybe, I don't know. Yeah.
So maybe first to comment on this. So I recently worked on this, and basically counting this is hard from a complexity perspective. So you can show something like sharp p-hardness results and that stuff. And I wanted to ask, like, do you have like a paper where you did this exact counting with Oscar?
Yeah, we have code for that. Yeah, actually, it was accepted as an official Julia library, right? So can
see that.
yes, sure. Okay, so where else can you use tropical geometry, right? So tropical geometry, as we've seen, I mean, I didn't show you anything about this, but basically you have an equivalence between tropical geometry in terms of phylogenetic trees with tropical varieties. We have equivalence between neural networks with tropical rational functions. And it turns out also that metric graphs, there's a one-to-one correspondence between metric graphs and tropical curves. Right, so in very recent work that, I mean, well, this has been like the work of like over 2 or 3 years by my PhD student Yuji. He studied these the computational questions between looking at this equivalence here, right? So the idea here was basically, can we use a tropical curve representation to say something and study metric graphs, right? Which are very important quantities, right, in graph theory. Like, so we've seen these are basically what are used to study traffic and road networks, what are used to model them, and they're important data structures, right? So yeah, so there's ways that you can do this, right? And essentially, what we offer here, right? So as I mentioned before, right, like the way that people look at graphs so far is basically in terms of combinatorics, collections of edges and vertices, right? But what we say here, right, is that using the tropical curve representation, right, we only care about the homology of your graph, right? So we're only defining a graph here in terms of its genus. And it turns out that this perspective offers a lot of things, right? So what we did was we defined new graph kernels based on the tropical representation here. So we don't consider graphs in terms of combinatorics. We look at its genus, and when you do it this way, it turns out that the computation is very fast. So there's 2 things to be careful about here, though. So it only works on real data in the label-free setting, right? Because this is basically what we get from the tropical construction. I think there might be ways around to get to adding labels if you wanted to, but it's a hard problem and requires a lot of thinking. The other one where it's basically kind of like pathological, there's no way that you can do it, is if your metric graph is a tree, right? You need to have holes in this case, right? Because otherwise it's going to be trivial, right? So that's an important limitation here. But most of the time, so for example, here, this is an example of what the road network looks like near the Victoria Station in London. You can add landmarks, and then the idea here is like if you add more landmarks, right, which can show up because it depends on how you're giving people instructions to get somewhere, right? If you're looking at it in terms of graphs, then the metric, the tropical construction works here. So that's another kind of nice application, I think, of tropical geometry, and where I think that tropical geometry has quite a lot to offer in terms of data analysis. Yusu, yeah.
So using only the homology seems to be very very strong because I mean there are a lot of branching that one cannot cover. But it seems that in practice people also use relative homology to kind of convert them. So can you incorporate that here?
Yeah. I think that would be a really interesting future direction. So yeah, this is something that I would like to work on next. This is quite a new kind of perspective, and so the first thing is like, does it work at all? And now can we enrich it with other things like also maybe relative homology? I think that'd be a really cool way to go. Okay, moving to applications a bit. So I mentioned before about neural networks and pure mathematics. So yeah, and in particular for GNNs, right? So as I mentioned before, this is something that my postdoc Sarah in her PhD used really just vanilla neural networks, right? Just looking at MLPs, right? So this is sort of like the most basic thing, and it turns out that you can get very, very powerful results. So she worked a lot in Fano varieties. So Fano varieties are important, right? You can think about them as the building blocks to Calabi-Yau manifolds, and Calabi-Yau manifolds have been sort of described as the key to understanding the universe, right? So essentially, you can sort of like look at these Calabi-Yaus. They're made up of Fanos, and then so the idea is if you understand Fanos, you understand Calabi-Yaus, you get insights into sort of the universe, right? My colleague Tom Coates at Imperial has been working on this Fano search project since 2013, where they're trying to build databases of these Fanos. So here are some examples of some Fanos, right? So you can see how different they look, right? So as I was mentioning before, like these varieties are very wild, right? But they're also very flexible in general, and this is why I think they make a lot of sense for modeling data, because you can sort of see the variability here. And now the question that they were interested in is, what's the dimension, right? So this is an important question. So we have this nice theory that a lot of people at Imperial work with, which is mirror symmetry, right? As the association between Laurent polynomials and Fano varieties. And the nice thing here is basically you have something that's computable, right, to an object with a relationship with an object which is sort of not, or more difficult to compute. And then essentially the idea here is that some quite powerful results using machine learning here that Sarah did, and is that you have the quantum period, which is an invariant associated with the Fano variety, and you have the relationship with the Laurent polynomial and its associated invariant, which is a classical period, and it knows the dimension. It basically carries all the information of the dimension and can detect terminal singularities as well. And this is very powerful because, it's quite, well, I guess, first of all, the indicator is that this is a pure math paper that ended up in Nature Communications, which is very, very rare for us, right? So that was already something that was, that I think is sort of like saying something about the power of neural networks in this case here. But like, it's also widely agreed on that like experts in the algebraic geometry field would say that this kind of result that Sarah was able to come up with conjecture discovery using neural networks with Fanos is not something that would have been able to be proven for the next 50 years, I think. So this is basically an argument basically saying that machine learning is very powerful here, and we can use this when we're looking at real data. So if you can do this already with just a standard MLP, right, what could you do with a graph neural network? And this is something that we're working on right now with Sarah and 2 students, right? So we want to use reinforcement learning graph neural networks to do conjecture discovery, and in particular, we're looking at a problem from graph theory of the Moore graph, right? So this Moore graph here is basically, so this here is this example, this is the Moore graph of what it looks like for the Moore graph represented, the Peterson graph represented as a Moore graph. And sort of what's known is that any Moore graph, right, there's like this theorem from graph theory that says any Moore graph with girth 5, right, so girth is basically the shortest cycle, basically it's like a regular graph whose shortest cycle length is more than twice its diameter. It has to have degree 2, 3, 7, or 57. Now, an important open problem here is, does a Moore graph with girth 5 and degree 57 exist? Don't know. And so we're trying to use graph reinforcement learning for that right now, and hopefully we'll get somewhere. I think this is something where it's, if you care about graph neural networks, this is also a very nice application area, right? Okay, so let's try to move on to topology for machine learning. This is going to be, so I'll try to sort of go over this kind of quickly, but the idea here is like what I mentioned before about topology is, right, you're looking at the shape, right? And here you only care about like connecting components and loops, right? And so you can express, these shape components with some combinatorial, but basically like the Betty numbers here by basically just counting the numbers of edge vertices and loops here, and you can compute this, and this is a kind of an invariant, right? Basically you can study this because like if you care about things about graph isomorphisms and things like that, Betty numbers and the topology and other topological invariance is very important and very useful in the setting. Yeah.
Sorry for being so skeptical, but why don't you just count cycles? I mean,
do you
don't need Betty numbers. I mean,
you can, right? But the idea here also is that like you have some sort of like there are some cases where you have some things that are sort of too restrictive, right? Or if you're looking at real data, again, it's very dependent on what the use case is and what you care about, right? So. I think I'm pretty sure that there are some cases where here you can just look at the number of cycles. Like, why not? Yeah, I agree with that. But if you come from like, okay, my side is the mathematician, right? I like persistent homology. I want to apply that there, right? And it turns out that that's been useful in some cases. But I definitely agree with you, right? Like I am not. I mean, the reason why I kind of like don't do only persistent homology and I'm open to other kinds of mathematics is that I believe in looking for like, okay, the right solution for your problem, right? Instead of turning everything into a problem that looks like what that can be solved with what you know, right? You should look at other things. So definitely agree with you, right? Like you are right to be skeptical. Maybe you can, right? But I'm going to just tell you now about like how some other machinery, right, can be used or has been useful in this case here. Okay, so I mentioned already about how, right, algebraic topology looks at global properties of spaces that are preserved under continuous deformations, right, smooth deformations. Data can be looked at some sort of like, continuous deformation, so this is why it kind of makes sense. And then the idea behind persistent homology, or basically topological data analysis, is basically looking at a dynamic version or dynamic evolutions of topological features, right? This is normally done over a filtration. And this makes sense for graphs as well, right? So we have these sort of like nice kind of like dynamic features here. So this here is a picture of a RIPS filtration. So there's lots of different types of filtrations here that we can look at. And it's basically looking at a way of sort of like, how do you measure the shape of your underlying space when you're having a discrete setting here, right? So in this case here, if you're looking at points that are sampled from some sort of underlying space and you want to learn about what that space might look like, especially if it has like holes or things, then this is where persistent homology makes a lot of sense. And it's an algebraic construction here, right? So you have this filtration, you want to compute a persistence module from that, from where you derive invariants, and the invariants are what you're going to use in your data analysis here, right? And there's this kind of like nice theory that's set up here. Basically, you have this kind of like inclusion set of your topological spaces based on your filtration. You can apply like the homology functor here, and then in the end you get this collection of spaces together with vector space homomorphisms, and then now you have this algebraic object, which is known as a persistence module. This has got nice properties. So one in particular is the structure theorem, which basically gives you interpretability. So you have your persistence module in the one-dimensional case can be decomposed into rank 1 summons, right? And then each of these indecomposables here correspond to one single topological feature in your filtration, right? And this basically gives you some sort of interpretability. So if you want to say something about what your data is showing to somebody who's like a practitioner, you can say that in terms of the shape here. So this is kind of nice. You have some sort of like, algebraic constructions. Here's like a theorem. It's quite, the proof is not easy, but it basically gives you interpretability. And you also have metrics between these invariants, right, which basically say that, okay, you can now do things like, whatever, gradient descent learning, statistical analysis, and things like that, because you have this. And then in particular, from these metrics, it gives you the second property, which makes this viable as, sort of data analysis, tool for data analysis, because you have stability. And what this basically means is that your invariant is a faithful representation of your underlying data. So this here has been used quite a lot in real data analysis, right? But here we care about machine learning, right? So where does this come in, and what is its place in neural networks, like machine learning, deep learning, and in particular graph neural networks, right? So, there's, like I was mentioning before in terms of graph embeddings, right? There's ways that you can actually take these invariants and then basically use them in standard practices by doing embeddings as well. So there's lots of vectorizations that exist also for persistent homology. You're taking this algebraic object, you map it into some kind of nice space where you can use standard methods. This to me, I think, is sort of cheating, as I mentioned before. But there's some history here, right? So these are sort of my favorite papers in this, because basically this is saying that, okay, we're not going to cheat here. We're going to actually take the algebraic representation of the persistence diagram itself and then create a layer in your neural network that inputs this, that intakes this directly. So this is sort of these are sort of the first works that I think that kind of made this viable here. And then in the case of graphs, right, you can actually develop also this topological graph neural networks, which is done by some people in the community here, where you can basically just take into these topological, looking at the persistent homology of your graphs here, and then encoding them into your graph neural network. And so this has been done. And why would we want to do this? So going back to the question of expressivity, right? So typical GNN architectures, right, are no more expressive than the Weisweiler-Lehmann test for graph isomorphism, right? So this is a kind of a classical result, which is known. But more recently, what's been shown is that persistent homology is at least as expressive, right, as WL. So this is sort of motivating why persistent homology can actually be useful in this case. Again, depending on what you want to do, right? You can absolutely be skeptical, right? It can also be too powerful, right? But I think in this case, in terms of if you care about expressivity, right, persistent homology wins in this case, or it can offer something more, right? So yeah, there's been a lot of work, but some of the things that, so I mentioned before, the Hoffer paper is the one. There's a paper that shows that topological features are very expressive, right? And then they use topological features or signatures in GNNs. Some other work that Yusuf and collaborator has done also is to integrate persistent homology into GNNs. More recently, this is what I think is quite cool, is using persistent homology to improve graph pooling, right? So the idea here is that you want to reduce the size of a graph by preserving its structural information, and the way that I see it is that persistent homology is really the tool for that, right? So it's this idea of basically just looking at your loops, but loops in terms of stable representations of your loops, and this works pretty well. So this was a recent paper from NeurIPS last year that incorporates topology into this, and so that works quite well. So moving away from graph neural networks just for a second, and the reason why is because I want to sort of showcase my students' work on this, right? So this is a question of generalization, right? So, there was a boot camp, which unfortunately I missed. I would have been very interested to hear about that. But generalization, the question here, generalization, I think, is sort of one of the key questions behind the questions of why does deep learning work so well? Why do neural networks work so well? And generalization is basically just a statistical question, right? So you have all this training, right? Your model's been trained a lot, and then you give it some new observation, right? And it's basically able to perform extremely well on that, right? And the idea here now is you want to study the generalization gap, right? So this is the gap between what's the empirical and the theoretical, or the population. This has basically been studied quite a lot. And line of work, pretty recent line of work, since 2020, has basically proposed a fractal structure for this optimization trajectory of your neural network, right? So fractals here comes from random dynamical systems. It's like an analysis thing. Disclaimer, I don't know anything about random dynamical systems, right? So this whole thing is I can't really say much about this, but the idea here is it relies on some sort of self-similarity here. But the thing that kind of caught my eye, and this is sort of when I started jumping on the machine learning merry-go-round, which was only last year, right, was when I saw this paper saying that fractal dimension is approximated by persistent homology dimension. So again, from my my position as a researcher in computational topology, right, I was like, okay, I know persistent homology dimension. Let's take a look at this. So some interesting work, I think, has been shown here, because they're looking at this problem of the generalization gap right, with persistent homology dimension. And there are some papers here that have been reported to correlate with the worst case generalization gap, and not only that, predict the generalization error. So this is quite a strong claim, right? Like it's basically saying that, okay, you can predict how well a neural network is going to do from persistent homology dimension. So I studied, with my students and together with Michael Bronstein, actually, we studied this quite a lot with a lot of experiments, and we weren't able to reproduce this claim. So in our experiments, right, this is kind of like a, maybe for the skeptics here, this is a kind of an argument about where you don't actually win anything using persistent homology. Because we basically showed that it turns out that the question, the problem is a lot more complicated than just looking at persistent homology dimension, and I think more needs to be studied. So in this particular case, it turns out that, you need to take into account things like hyperparameter tuning, right? Partial correlation. You should look at the conditional mutual independence as well. Basically this whole idea of fractal structure, like and generalization, fractal dimension and generalization, I think, is something that more needs to be said about that.
So fractal dimension is the same idea as the manifold hypothesis, right?
It's related to like the box counting dimension stuff. So yeah.
When people test the manifold hypothesis, they use this Bickel, this kind of fractal dimension with k nearest neighbors. No, this is what you mean?
Potentially, I don't know. I like I said, the fractal stuff, like that comes from random dynamical systems. That's not my area at all. I don't know that. Right?
Yeah, but if it's the one that I think of, it's always related to the manifold hypothesis.
Okay. Yeah. No, perfectly possible. I believe you. I just don't know myself.
So
right?
I guess that's as strong as the manifold hypothesis is.
Maybe. I really don't know. I can't say there. The one thing that I can say, the one thing that like I know about is the connection with persistent homology dimension. So that is something that I know about. But the actual place of like the fractal stuff, I'm sorry, I can't say anything about that. Okay, last few minutes. So another question that we care about. So this is sort of going back to graph neural networks, sort of, because we're looking at LLMs, right? And so if you're looking at LLMs as transformers are graph neural networks. Let's go back to this. The question is, okay, interpretability, right? So now the question is, okay, what is the topology of activations in an LLM, right, of the last token of some input prompt as it progresses through a fully trained model, right? Can we say something about, in the case of adversarial machine learning in this case? So this was a collaboration with my group with the Microsoft Security Response Center. And the idea here is we're looking at two different types of adversarial attacks in LLMs, right? So we looked at like kind of six different LLMs of different sizes, including frontier size LLMs. And the idea is like we looked at, okay, prompt injections, right, where you're looking at attacks which relate to data processing, right? So if you ask ChatGPT a question and it needs to go to the internet to look for its answer, for example, this is where attackers can basically inject false information and then basically kind of corrupt the answers that you're going to get. The other one is sandbagging or backdoor fine-tuning, and this is the part where once you have your sort of pre-trained model and then you're going into the sort of like the fully trained setting, right, where you basically want to have ChatGPT have conversations with you. This is the other place where you can have adversarial attacks, right? And basically in the case of backdoor fine-tuning, this is the place where attackers can basically deliberately make your model underperform. So we looked at all these models. There's this process here to compute persistent homology from them, but that was the idea. The idea is like, okay, let's compute persistent homology. And it turns out that for these two very different types of adversarial attacks, we're able to separate clean and poison data from each other, right? So this is sort of like opening the door to saying, okay, persistent homology can be a powerful tool to understanding adversarial scenarios, because with very, very different types of attacks, which the adversarial machine learning community would have to use different tools for the two types of things, assuming, again, that you know what type of attack you're looking at, right, which might not always be known. Here in this case, persistent homology is basically saying that you have a consistent deformation of these spaces under clean and poison data, and they behave the same way no matter, what type of attack you're looking at, whether it's the prompt injection or the backdoor fine-tuning. So yeah, so we see this kind of like, I mean, essentially the earlier layers, things are a little bit more sort of difficult, although you can still see quite a clear separation between clean and poison here, but they become very, very distinct from each other across layers, I mean, in the later layers. And sort of this is sort of an invitation to saying, okay, maybe we should look at persistent homology as a tool in adversarial machine learning as well. Okay, so coming to the end, right? So wrapping up, final thoughts, right? So I mentioned, so I started off this talk basically by saying you can't really look at geometry in graph neural networks and separate them from algebra and topology here. So there are three lenses on geometry, or three lenses to sort of enhancing your GNNs here, right? But for me, I also see them as sort of three superpowers, right? So the idea here is that you can enrich your models by adding features using algebra, topology, and geometry before you actually do your sort of like processing. So the idea now is basically, okay, you can enrich your models, add features before message passing, you can constrain your architectures and define new kernels and do lots of things here. And there's a very sort of like natural language in all three of these sort of mathematics in terms of symmetries, invariance, connectivity, higher order features, metric invariance, curvature, embeddings, all these kinds of things to GNNs. And yeah, so these are the papers that I cited in my talk. I want to mention, so there are 3 pages of cited papers here. So if, I'm aware that like there's been a lot of work, amazing work that's done. So if your paper hasn't showed up here, please don't be offended. It doesn't mean that I don't think your paper is amazing. There's only just so much. Well, we only have 24 hours in a day to read papers. I actually spend quite a lot of time reading papers. I wish I had more, but yeah, there's more. So these are the papers that I actually cited in this talk. If you're interested in this and you want to read some more, there's a lot of cool stuff. So these are some of the papers that I like a lot. So papers and books also, right, of course. So the geometric deep learning book is a big one. If you want to get into algebraic geometry, I love this book by Cox, Little, and O'Shea. So that's one. There was a very recent paper in the ICML just now, which basically provides a dictionary between ideas between algebraic geometry and things you would look at in sort of machine learning. Topology, right? So you have topological deep learning and relational learning. So these are kind of references. But basically, if you are interested in this stuff also, like I would look at basically any work by Uli Bauer, Chao Chen, Michael Josvik for the tropical geometry, Roland Quit, Lekhang Lim also, I'm a big fan of his work. Yu Ren, Bastien also is really big, and then Yusu here also has amazing work in this area. So this is if you're interested. And then this is the part where I advertise work by my students and postdocs. So everybody in blue here is the student or postdoc that I've had the great pleasure of being able to supervise and learn from as well. So with that, I need to thank my students and postdocs, but also thank funding. So I get money from the UKRI and Cancer Research UK, and thank you also for listening to my talk.
Thank you for the very nice comprehensive talk. So I'm wondering, for example, you mentioned fractals, and I think a lot of these topology ideas seems to show up more on the expressivity side. But on Wednesday, we talk a lot on like generalization, especially out of size generalization or out of distribution generalization. Can you maybe comment or remark on whether some of these ideas, or maybe it's already in some of the paper that you cited, that did people maybe impose or assume some topology structure and then to say something about generalization?
So the short answer is I don't know, right? But I am aware of some papers, very recent papers that came out this year and last year, kind of actually in response to our paper, which basically shows that, topology kind of doesn't work. And then there are other things where they looked at different topological measures, so including magnitude is another one. It's completely different from persistent homology. It's a completely different kind of invariant that has roots in category theory, actually. And there's been some work that's looked kind of promising there. I don't know the details of that, but yeah, maybe, I think. So, I mean, I think that the fractal stuff, again, as I mentioned before, I don't know anything about random dynamical systems, but I think that that idea came up because you have this self-similarity, because when you're sort of training, right, everything is kind of depending on what you saw before, right? These are not independent processes. And so self-similarity kind of makes sense in that case because, you know, also in terms of fractals, you kind of looking at a refinement where everything looks the same as on the course level.
Right, because this reminded me of, for example, Yushin's talk about the size generalization, where
Yeah.
you want to embed some smaller graph into the bigger space. So one way to she embedding is to duplicate entry.
Yeah.
So in some ways, then you have cell similarity.
Yeah,
So,
yeah.
so-
I mean, I think that makes sense, right? Like, I mean, I think the sort of logic about, you know, using fractal structures, you know, makes sense here. I just wasn't able to read that original paper because I don't have the background in that. I think the main thing, yeah, as I mentioned, the main thing that I saw was the connection to persistent homology dimension, and that is sort of the area of mathematics I work in. But, you know, I think that the fractal stuff is, you know, I mean, or at least, you know, like, I mean, I think generalization is, of course, you know, one of the most important questions. And, you know, in terms of using the kinds of mathematics that I motivated, yeah, I mean, I know some more has been done that is very, very recent that I haven't read in detail yet. Probably more can be done, I imagine, or I hope. Yeah. Yeah.
So you mentioned that a very nice idea that I didn't know, which was that you have this idea, these tools to take a persistence diagram and then keep it kind of fixed and simplify the data set, right?
Well, I mean,
is there structural properties you say something like that?
Yeah. So I mean, one way that people have been using persistent homology, right, is they've been using it as a summary of your data, right? And so the idea is like you compute persistent homology on your original data, and then instead of doing the data analysis, you do your data analysis on the persistence diagrams themselves.
But are there results that really do simplify, remove points or move them or do something on the data set that with the aim of not removing keeping the persistence diagram almost the same, but then simplifying or making nicer the data?
I mean, I don't think it's exactly simplifying or keeping the data nicer, but one approach that I'm aware of that's used quite a lot is this method of sparsification, right? And so the idea is like, okay, you can kind of like sparsify your original input data, and then you get a faster computation of your persistence diagram. So this is implemented.
But with the aim of getting the persistence diagram.
Yeah. So the idea,
I was wondering if the inverse, you know, I have a diagram and I want to move, like, you know, for example, when you have this thing with the over squashing, that would be an example where you have to keep some property and then you want to change a little bit your graph to make it nicer, but the property like the shape or something has to be fixed, right?
Yeah.
So a task, I don't know of a task like that. I thought there was a hint in the way, but maybe I misunderstood it.
Well, I mean, I mean, this general question of, so most people, right, like they go the other direction. The idea is that they're basically using that, right?
It's
but
harder, the one that I mentioned. Harder because it could be hard to differentiate, to do the backpropagation.
Yeah. So, I mean, one thing that I'm aware of in a paper, quite recent paper by Peter Bubenik, right? So Peter Bubenik proposes one of the most famous vectorizations of persistent homology, which is known as a landscape, where, so a lot of these questions, people kind of like looking at these kind of vectorizations of these different representations, they're asking, is this injective? Right, and then not only that, he basically shows that an inverse exists here. So theoretically, you could go back, right? But yeah, I mean, this is a.
It would be interesting to try to fit it to backpropagation.
Yeah, I think so. But I think that will be very difficult. Maybe
There's
use
an inverse problem that you can actually modify the persistent back and then drive through the differentiable layer, and then you have to change the input so you get an ideal persistent diagram. There is already work on that.
Yeah. But I mean, in general, I mean, I didn't motivate it enough. But persistent homology is quite difficult to work with because the space of persistence diagram you get is a very complicated geometry, and the construction itself is very algebraic. But you know, I mean, you do have. I mean, it still works in some settings. So, but yeah, it's a hard question, I think.
Okay, then let's thank the speaker again.